Have you ever wondered how we are able to detect different smells? Well, our sense of smell relies on the shape of molecules. And each molecule that we smell has a unique shape which fits into a unique odor receptor in our nasal cavity. For example, the smell of coffee comes from a molecule that fits into a coffee molecule detecting receptor in our nasal cavity. And the smell of fresh baked cookies comes from molecules that also fit into their counterparts in our noses. So once that specific molecule binds to this active site, it sends a message to our brain that tells us what we are smelling. So the shape of the molecule is essential to determining how it functions. The shape of the molecule also affects a lot of its other properties. For example, its boiling point, its melting point, its solubility, and its chemical reactivity. So in this lesson, we are going to use Lewis structures and the VSEPR model to predict the three-dimensional shapes of molecules. So what does VSEPR stand for? It stands for valence shell electron pair repulsion, which is kind of a mouthful, but all it really means is that electrons are not going to want to be next to each other. So they're going to do everything they can to be as far apart from each other as possible. And that's where the repulsion comes from. The repulsion of electrons is what determines the shape of the molecules. So it's important to know where our electrons are, and that's why we're going to look at the Lewis structures for this. Once we know where the electrons are in the molecule, we're going to determine where they're actually positioned so that they can be as far apart from each other as possible. And in this video, we are only going to look at molecules with no lone pairs on the central atom. So let's take a look at a really simple molecule. I want you to draw the Lewis structure for carbon dioxide. So hopefully this is what your structure looks like. We have carbon as our central atom and two oxygens on either side with double bonds connecting the carbon and the oxygen. Now you're going to notice that the central atom does not have lone pairs on it. The oxygens do have lone pairs, but the central atom, carbon, does not. You'll also notice that the central atom, carbon, has two regions of electron density, one at one double bond and one at the other double bond. Remember, bonds are just electrons. So if we have a bond, we also have a region of electron density. So what we're going to do is take a look at the three-dimensional structure of molecules that have two regions of electron density on the central atom. So I built a molecular model of carbon dioxide. You're going to see the double bonds from carbon to each oxygen, and you're going to notice that this molecule forms a linear shape. And that's the name of that shape. That's the name of the molecular geometry and the electron pair geometry of this molecule. So what do I mean by electron pair geometry? And what do I mean by molecular geometry? Well, electron pair geometry takes into account all of the regions of electron density, which include bonds and lone pairs. The molecular geometry just takes into account the bonds. Now, the lone pairs participate in the movement and the shape of the molecules, but the molecular geometry will only identify what that molecule is doing and what it looks like with the bonds. So we have the electron pair geometry, which is the bonds and lone pairs, and we have the molecular geometry, which accounts for the lone pairs, but doesn't exactly describe the shape of the molecule with the lone pairs. More on that later. One thing I want you to pay attention to with these molecules is the bond angles here are 180 degrees. So from here to here is 180 degrees. And those bond angles are going to be important once we get into bigger molecules and molecules that contain more than one central atom. Now I want you to draw BH3. So draw the Lewis structure for BH3. Okay, hopefully you have something like this. Now, the three-dimensional structure of that molecule might look a little different than your drawing. So this is the three-dimensional structure of BH3, and you'll notice that it exists in a plane, so it's kind of flat looking. And if we were to turn it, we would have three kind of spokes outside of that central atom, and all of those spokes are 120 degrees apart. And that's because this exists in a plane, and if we were to divide that plane, that 360, into three equal portions, we would have 120 degree angles. Now, why is this 120 degree angles, and why are they three equal portions? Well, that goes back to the valence shell electron pair repulsion. These three regions of electron density are going to want to exist as far apart from each other as possible. So they exist 120 degrees apart from each other. Now, this molecule has three regions of electron density, so three bonds on the central atom, and it has no lone pairs. So the name of the electron pair geometry, because it has three regions of electron density, is trigonal planar, meaning it has three sides, but it exists in a plane. The molecular geometry is the same as the electron pair geometry because there are no lone pairs on the central atom pushing these bonds in other directions. So the electron pair geometry and the molecular geometry are both trigonal planar. The next molecule I want you to draw a Lewis structure for is CH4. And this is where our Lewis structures are really going to start veering from our VSEPR structures or three-dimensional structures. So hopefully your Lewis structure looks something like this, and you're going to notice that the bond angles in your Lewis structure are probably 90 degrees. Now, in reality, this structure exists in 3 dimensions, not 2, like our Lewis structure is in 2 dimensions, but the VSEPR structure, or the three-dimensional structure, is in 3 dimensions. So we have extra space to work with. And it requires a lot of math to figure this out, and I'm not going to go into it, but in 3 dimensions, if these regions of electron density are going to be as far apart from each other as possible, their angle is going to be 109.5 degrees. So from here to here, and from here to here, and from here to here, they're all 109.5 degrees. That is the distance, that is the bond angles in this molecule. Now we have no lone pairs on the central atom, and we have 4 regions of electron density. So our electron pair geometry is called tetrahedral, and because we have no lone pairs on the central atom, our molecular geometry is also tetrahedral. Now I would like you to draw the Lewis structure for PCl5. Hopefully your Lewis structure looks something like this. And this is really where the 3-dimensional and 2-dimensional structures will differ from each other. So the 3-dimensional structure of PCl5 looks something like this. So you're going to notice, see if I can line it up here, that in this plane we have bond angles of 120 degrees. Okay? And if I were to rotate it, in this plane, we have bond angles that are 90 degrees. So depending on which plane we are looking at, we're going to have different bond angles. And that is, these are the bond angles that are required so that the electrons can be as far apart from each other as possible. Remember, valence shell electron pair repulsion. And electron pairs are those bonds there. So we have 5 regions of electron density on this central atom, which gives us an electron pair geometry of trigonal bipyramidal. The trigonal part you can see if I hold a molecule like that, and that's the trigonal portion of the name, and the bipyramidal portion of the name kind of comes in the sense that we have two pyramids. We have a top pyramid and a bottom pyramid. So this is trigonal, and then the bipyramidal is the two pyramids, the top and the bottom pyramids. So if these electrons need to get as far apart from each other as possible, and there's 5 regions of electron density, this is the shape that that molecule is going to have. Now the last one that I want you to draw is sulfur hexafluoride, or SF6. Hopefully your Lewis structure looks something like this, and the three-dimensional structure is quite a bit more complicated. So this is the three-dimensional structure of SF6. Imagine these are fluorine atoms, and this is our sulfur atom in the middle. One thing you're going to notice is if we turn it on this plane, we have bond angles of 90 degrees. And if we turn it on this plane, we have bond angles of 90 degrees. So every bond angle, aside from going across the molecule, every bond angle is going to be 90 degrees. So if we have 6 regions of electron density, we have 90-degree angles to get those electrons as far apart from each other as possible. So the electron pair geometry here with 6 regions of electron density is called octahedral. And because there are no lone pairs on the central atom, we have a molecular geometry of octahedral as well. So having no lone pairs on the central atom will give you the same electron pair geometry and the same molecular geometry. In a later video, I will discuss how having lone pairs on the central atom changes the shape of that molecule. And further, we'll discuss what happens when we get really large molecules. How do we determine the shape of a very large molecule?